All right, so just going to look at integration by parts and where it sort of comes from. So if we look from the previous video at the product rule, this is one way we can express the product rule. ddx of two functions u and v, which are both functions of x, equals u dv dx plus v du dx. So go have a look at the previous video if you want to understand that in a little bit more detail. But what we can do from here is we can come up with what's called integration by parts. So if we were to take the integral of both sides, we take the integral of this term here, and then we take the integral of the right-hand side. Now remember, the integral of a sum is the sum of the two integrals. So yeah, you get the integral of u dv dx plus the integral of v du dx. Okay, it'll become clear why this is important in a moment, but what we can do from here is we can yeah, look at this left-hand side. If we take the integral of the derivative of uv, well, integration and differentiation are inverse operations. So you're just left with uv, and the right-hand side stays the same. And so what we'll get is, if we just rearrange things a little bit, if we bring the u dv dx to the other side, well, actually, a better way to think about it is the integral of u dv dx, and then we take this, we subtract this term from both sides. So we get u dv dx, the integral of u dv dx equals uv minus the integral of v du dx. Okay, and you're probably wondering why on earth that's an interesting result. Well, what it can do is it can help us find the integral of a product of functions, right? So what we've got is u dv dx. This is telling us how to find the integral of u dv dx. So let me explain. If we've got an example like this, where it says find an antiderivative of x multiplied by e to the x, well, what we can do is we can say to ourselves, all right, let's make this first function u, which call that x, and therefore the derivative is du dx, which is just 1. Okay, because the derivative of x is just 1. Okay, and then v is e to the x. So dv dx is e to the x as well. Remember, when you take the derivative of e to the x, you get e to the x. So therefore, if you take the antiderivative of e to the x, you also get e to the x. Okay, and then now what you need to do is apply the product rule. Oh, sorry, apply the integration by parts. We're going to apply this rule down here. So we're going to get the integral of u dv dx. So x multiplied by e to the x. That's going to equal u times v. So x times e to the x minus the integral of v, which is e to the x multiplied by 1. So that's just e to the x. Okay, and what you'll notice is this integral here is actually computable because we know that. Okay, so we'll get the integral of x e to the x dx equals x e to the x minus, all right, this integral here is just e to the x, but don't forget the constant of integration. So you have to plus c when you take the antiderivative of this. And yeah, that's an example of applying integration by parts and sort of why it's useful. Sometimes you'll need to apply integration by parts more than once in the same question. So it's something just to be careful of, because, for example, if this thing here was still not differentiable, sorry, was not anti-differentiable by sort of the rules that we know so far, we would need to use integration by parts again. So just keep that in mind. Okay, again, finish with the problem. So find an antiderivative of x multiplied by tan squared of x. So it's an interesting looking graph. You don't really need the graph to answer this question, but you definitely will need to use integration by parts. So yeah, see if you can come up with an antiderivative of this function using integration by parts and let me know how you go. Good luck.